Hey, it's Horner, and here we go with number 6. So this is number 38 in the book. We have 4 identical conducting spheres, and they're all very well separated from each other. The initial charge of W is 0, and they then tell us that we touch W to A. So in step 1, we're going to take W, we're going to touch it to A, and to find out what the overall charge is, then, since they both will have the same charge, we're going to add the 2 and divide by 2. We know that QW is 0, and so because it's 0, when we add that to QA over 2, we end up with a value of QA over 2 for our particle W. Now what we're going to do is we're going to touch W to B. And initially, they tell you that B has a charge of negative 32e, and C has a charge of positive 48e. And remember, A in the beginning, we don't know what that is. So, but we do know that we're going to be able to go through and find out what A is, because in the end, they told us what W is going to be after we do all these things. So we're going to take that QA over 2, which is the charge on W. So after the first time that it touches this other one, because this one was 0, we know whatever the charge on A was divided by 2 is going to be what W has. So this one now is W again. So this is really QW. That's kind of what that stands for. Plus the negative 32 charge on B. Going to divide that by 2. And when you do that, you get QA minus 64 divided by 4. At this point, now we know that this is W's new charge after step 2. So now it's QA minus 64 over 4. So after the first step, that's it. After the second step, that is its new charge. Now for the third step, we're going to take this thing and we're going to touch it to this. So now we need to find out what is the charge after we do that. So we're going to do QA minus 64 over 4 plus 48, and we're going to divide by 2. And when we're done, we remember that the final charge on sphere W is 18. So that's why that 18 is there. It's because we know the final charge on W is 18. And W has become this big thing, which is equal to 18. So now at this point, it's just going through and doing the rest of the math. And once you go ahead and you'll notice we multiplied both sides by 2, and we get this. Then we went through and subtracted 48 from both sides, and we get this. Then we multiply both sides by 4, and we end up with this equation. And then we just add 64 to both sides, and we find out that the original charge on A is positive 16. For the next one, which is number 7, this one looks a little weird, but it's actually not too bad. So we have a charge of particle 1 being positive 4e. That just means an E is a fundamental unit of charge, and it has a value equal to 1.6 times 10 to the negative 19th. So with that charge, that's kind of like pi. So you can think of, you know how pi is a constant of 3.14 and it goes on and on. This is also a constant. It's just the constant for one single electron or one proton. They would have that charge. So that's why this E is there. And then down here, we know that this one is positive 6e. And because of that, we know they're pushing each other in opposite directions. So this 6 is going to push 4 up that way, and the 4 is going to push 6 down to the right. But you'll notice that it's on a surface. So really, all we're going to do is find the x component of the force of particle 2 due to particle 1. So we know it's going to move it in that direction. So the first thing we need to do is say, well, the force of 2 on 1 is equal to K times Q1, Q2 over R squared. That's our given equation, so that's nothing new for it. And then that is equal to K, Q1, Q2, all over the distance between them, which has got to be this line right here that I drew in. And that's just using the Pythagorean theorem. We also need to find out what is the angle down here. And so we could have done this angle or the one up here, but I just chose this one, and that would be the inverse tangent of the opposite over the adjacent. And when I plugged the numbers in, I got an angle of 18.43. So that's what this theta is. So now we have our equation, and we just want the x direction. And because we have a line like this of force, but we really just want the x direction, and we know this angle right here, we can say this is the adjacent side, this is the hypotenuse, so we want to use cosine of the angle times whatever the hypotenuse is. So this is going to be our hypotenuse, so that's the actual force times the cosine of the angle, and that'll tell us what our value is for the force in the x direction. So I just plugged everything in, 9 times 10 to the 9th. This Q1 is 4. You'll remember that's 4, but it's 4e. So it's 4 times 1.6 times 10 to the negative 19th. And then the other charge is 6 times 1.6 times 10 to the negative 19th. So all that's on the top, times the cosine of 18.43, because we found that here. And then we're going to divide by the distance between them. And once you do all that, you get 8.29 times 10 to the negative 25th newtons, and we know that this is pushing it to the right. They might also say that another correct answer is negative 8.29 times 10 to the negative 25th newtons, and the direction is here. That just means that it is opposite of the particle. So that means it's getting pushed away. So that is the question number 7. This is question number 8. And for question number 8, they want us to show that the distance between these two particles after they touch together is going to be this equation. So after that, then they want us to find out what is the charge on each one. So we're going to start first by thinking about what is the charge on the two after they touch. Well, if this one is Q and this one is Q and they touch, then we know we just add the two charges together, divide by 2. So after they touch, each one is Q over 2. So now the new charge is Q over 2 for this one, and it's Q over 2 for this one. But because this is a system and it has the two spheres, which have a charge, we know there is a force between the two, and that's the force of electricity. And so we're just looking at just this left side. And when we look at just the left side, we know the right side does the same thing, but we're just going to look at the left side. This ball is getting pushed to the left by the electrostatic force, or the force of electricity. We know mg is pulling it straight down, and we know that tension in this string is pulling it up to the right. So the only thing I have in the diagram that's not up and down or left and right is the force of tension. And they told us that there's the angle. So if we know the angle, we could say that in the y direction, the force in the y, or the force of tension in the y, is t cosine of the angle. And the force of tension in the x is, and this should be just ty, I guess, if we want to do that. We could make this other one just tx. So here we've got tx. There we go. T sine of the angle is the tension in the x direction. Let's go ahead and we're going to move down a little bit here, and we're going to say, okay, we have an equation for the force of electricity. And I know that that's 1 over 4 pi epsilon naught, which remember, that's also K. But because of the way that they want our equation, we have to use this. Times Q1 times Q2. But these two things are the same. So what you can do is you can write this as q squared over x times 1 over 4 pi epsilon naught. And so wherever you see this q1, q2, we made that into q squared. So let's go back over here, and we know that in the x direction, there's no net force. So we know that the force of electricity pulling this one to the left and the force of electricity on this one pushing it to the right should be the same. So we want to find out what this is. Well, we know that the force of electricity left and t times the sine of the angle going right are in opposite directions, but they should be equal. So we say t sine of the angle minus the force of electricity is equal to 0. And then I just move that force of electricity to the other side, and I see that t sine of the angle is equal to the force of electricity. In the y direction, which is up and down, we see t cosine of the angle, and we have mg, and I know those are equal and opposite, so I can do the same thing. T cosine of the angle minus mg equals 0, so t cosine of the angle is equal to mg. And because we have these two equations, we can do one of two things. We can either solve for t in one and substitute, or we can just divide the two equations by each other. So that's what I ended up doing, is I said t sine of the angle is equal to Fe, so there's this one, and I divided it by this equation. So t cosine of the angle is equal to mg. So now what we can do is we can come down here and we can say that the t's cancel, sine over cosine is tangent, and we still have Fe over mg. But they also gave us a little hint up here. It says, assume the angle is so small that tangent of the angle can be replaced by sine of the angle. So that's what we're going to do. So for small angles, tangent of the angle can be replaced by sine of the angle. So instead of tangent of the angle, we're going to replace that with sine of the angle. And that's equal to Fe over mg. Now, if we go back up to this triangle, we'll see that the sine of the angle can be equal to the distance left to right, which is x, divided by 2, because we really are just looking at all the lengths of this side of the triangle. So this is x over 2, this is L, and if I think about that angle right there, that angle would be sine of the angle is equal to x over 2 over L, or sine of the angle is equal to x over 2L. So now that I have a definition for sine of the angle, and that's just equal to x over 2L, that's what we're going to do, is we're going to say x over 2L is equal to Fe over mg. Now what we need to do is we're going to go from here up to here, and we're going to plug everything in. So now I've got x over 2L. I need Fe. So remember, Fe is on the top, and Fe, we said, was 1 over 4 pi epsilon naught times Q1 times Q2 over x, and this should be squared. Sorry about that. So that's what we've got here. But we also said that Q1 times Q2, they're both the same, so we just make it Q squared. Then I'm going to go ahead and move the 4 pi epsilon naught to the bottom and the x squared to the bottom. So now we have x over 2L is equal to Q squared over 4 pi epsilon naught mg times x squared. Now we're just going to rearrange some things. So when we rearrange this equation for x, we're going to multiply both sides by x squared. That makes it x cubed. I'm going to multiply both sides by 2L. So I did that. When I set this all up, notice the 2 cancels. That gives me 2 pi epsilon naught mg on the bottom. And if I want to get rid of the cube, I just take the cube root of this side. And that is what they wanted us to solve for. So this matches exactly what we have up here. Now that we've done that, we can plug our values into this equation and solve for q. So I rearranged it for q. We just did the square root of 5 times 10 to the negative 2 cubed. And that would be 5 times 10 to the negative 2 cubed times 2 pi times epsilon naught, and they give you a value for that epsilon naught, which is right here. So you'll have to find that value, and then 0.01 times 9.8. So we've got everything in there that we need. We need to divide now by 1.2, and we should get a charge of 7.5 times 10 to the negative 5th coulombs. For number 9, this one's a little easier to do. So we've got 3 arrangements of electric field lines. And the rule here is electric field is the number of lines in a certain area. So notice if I'm going to make this rectangle here, let's make it purple. So I'm going to make this one purple. If I look at that area and I look at this area and I look at this area, those 3 areas are all the same area. We're going to assume they are. Notice that there's 1, 2, 3, 4, 5 lines within that box, but here we only have 3, and here we have 3. So I know that A has the most lines within a certain area, so its electric field is the biggest. For the next one, when I look at A and B, I notice that A for this size box and B for this size box, A is bigger than B, but here both A and B are the same. They only have 1 line. So if I add those two, I only get 1 in each. Here I get 3 plus just that 1, so that'd be 4. So 2 is less than 4, which is less than 5. So what we're going to do is we just know now that A has the biggest field, B middle, and C has the smallest field. Then what I did is I grabbed the answer through kind of an answer key type thing, because this explains why the momentum is the same order. And basically all it is if I have a particle moving from A to B, that means that the bigger the electric field, the faster it will move. Why is that? Well, it's because work that is done on a charge in an electric field is equal to Q times the change in the potential. Because you don't know about that, the best thing you can do here is think about these electric field lines and use this as your kind of reasoning. So the bigger the electric field, the faster it's going to go, and the faster it goes, the more momentum it has. So that's kind of how you can think about that one. And then we're going to go down here. This one is number 10. This one's kind of nice because it looks super complicated, but it's actually pretty simple. We have these 2 square, and they call them arrays, of charged particles. The squares centered on point P are misaligned. So that just means that this one has a little bit of a turn to it. The particles are separated either by a distance d or d2 along the perimeter of the squares. So you can see how those charges are separated. They want to know what is the magnitude and direction of the net electric field at point P. So when we look at these, we had another one similar to this. And if you notice, the charges that are on opposite sides of P, so the distance from here to here and the distance from here to here are the same, and the charges are the same, that means that the two cancel each other out. Because the pink 3Q and this pink 3Q are equal and opposite from P, they cancel out. Same thing with the negative 2Qs here. Same thing with the negative 3Q and that negative 3Q, this plus 2Q, that plus 2Q, this negative blue, and this negative blue Q. But we do have a negative 2 here and a negative Q here, and there's a difference between the two. All the others we can ignore. And to find the net electric field, the equation for the electric field is just equal to K times Q all over R squared. For the net electric field, I'm going to do this for the negative 2Q and the negative Q and subtract them, because that'll give us the net electric field. So this is K times Q2Q over R squared minus K times Q over R squared, and that gives us our answer, E, is equal to K times Q, because 2Q minus Q is going to give you just Q, divided by R squared. And we always think about the electric field going from a more negative to a less negative for this one. So this one, the net electric field is actually going to what it seems to be to the right. And so that is the end of this homework.